some good questions about the chemistry here, and if there was leaching from the bottle of some polymer or some additive in the polymer. It's probably done by now, so it's probably pretty safe, is my guess. Or maybe things degrade just very slowly. So so some interesting questions there. Anyhow, this is where we left off last time. We're gonna continue with a little bit of kind of equilibrium chemistry, what's going on with that, touch on activity, kind of take a look at what is activity, why does it matter, and how are we going to calculate stuff with that, and then get into a little bit of acid-base. So we have a couple more example things to work through. Like I said last time, we will, I'll get a homework assigned for you by next time. I'm going to pull up the syllabus real quick. I did a tiny update just to kind of reflect where we are on the schedule. Because we had the slight rearrangement with the snow day, originally we had some sort of a MATLAB session kind of planned somewhere around the 4th or the 6th. So I just kind of rearranged that a little bit. So today we're going to talk about these activity corrections, introduce some of the acid-base stuff. So by the time exam review comes around, you'll have finished a homework that'll kind of encompass everything we're doing with acid-base and with the equilibria thermodynamics kind of stuff. Okay, so that's the plan for now. Keep in mind, you should have been progressing on the MATLAB stuff. I think at least the first completion assignment was due probably Tuesday, right? So whatever I've posted so far, keep up with that. I still reserve the right to shift some of the learning assignments backwards a little to give you a small assignment in between things, nothing overbearing, but just to maybe a little practice session to say, okay, solve this simple problem in MATLAB or something like that, right? Give you a chance to build on those tools a little bit. Okay, but I'll announce that. I'll talk to you about that if we do anything in that regard. All right, so last time we kind of introduced the fact that temperature can change our equilibrium constants, and really what we're after is understanding the K. The K is that equilibrium constant that's going to define where we are with the balance. How much of one substance do we have, or how much are we shifted towards reactants versus products, given that the rates need to find some equilibrium. So we can use the Van 't Hoff equation to solve if we wanted to find, let's say, the K value at a new temperature, maybe, and we know the K value at temperature 1, which oftentimes we can do or we can solve if we say that's the standard temperature, 25 Celsius. So maybe let's just say for a moment, if this is the standard temperature pressure condition, and this is the unknown, we could rearrange this equation very easily to say log of K2, which is our unknown, is equal to delta HR naught divided by that 2.303 R times 1 over T1 minus 1 over T2, all that plus log of K2. So if we know, excuse me, I forget one, sorry.
Is the subscript in delta H, the R, does that mean just for the reaction?
Yeah, that subscript should mean the reaction. Good question. So you can see we can solve for K that way, right? And we could potentially solve for a temperature also if we knew the equilibrium constants. So we can manipulate this, just do a little bit of algebra, whatever we need to handle that. And to get rid of the log, we could raise both sides, 10 to the power of both sides. That gets rid of the log, and we could then solve for the K values, or the K2. So hopefully that strikes you as, oh, maybe I've done that before. I think we could do that. So we could come back to this gypsum solubility problem from last time. I'll bring up the other slide and get the number here in a moment. But the question asks, by how much does the solubility of gypsum at 40 Celsius differ from the value we found at 25 Celsius? So what we're asking really is what percent or what multiplier do we need? Is it 2 times? Is it 1.3 times the value? What is the difference there? Give us some quantification of that difference for this gypsum reaction. Last time we calculated our K at 25 Celsius. Let's just call that K1, okay? And I'm gonna go pull up the other slides and find that exact number unless one of you has it in front of you, tell me. But with that, we should be able to use this equation and solve for it at 40 Celsius. Remember that this should be in kelvins. Temperature should be in kelvins as we manipulate that. And the conversion there is when we say degrees Celsius is going to be equal to the amount of kelvins plus 273.15. Okay, so that's the conversion. So I'm going to find that value for us. I'll give you a few minutes to work on that. I think we need the R value too, right?
Isn't the 0.008314?
I believe that's right, 8314. That sounds correct. I also will find that.
Is that in terms of joule per mole Kelvin? Right.
I think you're right on that. It's kilojoule per mole Kelvin. So R is 0.008314 kilojoules per mole Kelvin.
Is the
Yeah. So one thing that I probably should have highlighted previously, this is a good question. When we say delta G for a reaction, it's actually really going to sound very intuitive when I say this. When we say delta, that's the change after something happens. So the change when the reaction happens is going to be the delta G, the energy of the products minus what we were reacting. So it's the products minus reactants. The same will hold true for the delta H for the reaction, right? So the delta there, we know delta as the difference, right? That's mathematically how we use it. So the difference in the reaction is before and after, right? So in the same way, when we say delta H, that'll be that difference. So we take the delta H for the products minus the reactants. Oops, sorry. Oh no. Not sure what I just did, but I erased all the notes I had written on here, so I'm going to work on putting those up. Take a couple more minutes. Sorry about that. So once you find the K2, what you want to do is then make some comparison. So quantitative comparison, you could divide one by the other. You could do some form of that to say which one, to make a statement of how much does it differ. Relatable. Okay, so I'm going to start putting this into Excel. So you can just kind of follow along, complete it if you haven't yet. I'm just starting with delta H here. Did I do something wrong here? Are you?
Dude, I keep doing this backwards, dude.
Good? Okay. Okay, so T1 is 298.15. Oh, thank you. Good catch. 208, all right. And then T2 would be 313. Yeah, thank you. All right. Plus.
Dude, and the gas concept needs to be switched to kilojoules though. Because that's in
Okay. I think I did this a little messy, but I think that looks probably correct. Well, let me do this. Okay. How are we doing so far? Did you get this number? Something close? Okay. Maybe? Getting there? Okay. You said that K1 was 4.69.
Oh wait, the gas constant is in terms of kilojoule per mole?
Yeah, so it's kilojoule per mole Kelvin. could say like it's 2% smaller, basically.
So why is it that the rate gets smaller when the temperature is increased though?
It's not the rate that got smaller. This is a very good question. The question was, why is it that the rate got smaller when the temperature increased? It's the ratio of the forward and backward rates, right? So we actually have two different rates that are happening there, and it's a little bit unknown to us about how that balance shifts, right? Is one more likely than the other? Well, that gets into some really in-depth chemistry, right? It's not always intuitive that, you know, a lot of things are intuitive that like, oh, if the temperature increases, the rates typically increase, right? The rate of some reaction. But because we have two reactions, one's backwards, one's forwards, we need to calculate it like this and kind of see for ourselves. So if I've done all that correctly, and I forgot to bring the book with me. This is from that smaller book that I have. So, but I'll double check that. But this feels right to me. It should be pretty similar. A 15, 20 degrees change in temperature is probably not going to have a huge impact on an equilibrium constant like this, but it would have an impact. We good on that? Does that make sense? Okay. I didn't feel like I did the best job with Excel here. It probably would have been helpful for me to go ahead and define the R equals something and call all of that into the equation, but I think I got the equation okay. All right. Okay. So one other thing we can do with our our equilibrium constants is we can actually combine them when we have multiple reactions happening. So if we have some combination of a few things that are going on influencing the same system, we can combine them by essentially, when we add two reactions together, we're multiplying the equilibrium constants. And we can get a new equilibrium constant for the combination of the two reactions or the two equilibria. And sometimes that's quite convenient if we have a lot of stuff happening in one system. For example, iron hydroxides form pretty quickly, and we can go from Fe3 plus OH minus and add an hydroxide to it. So then we're now at 2 plus for that molecule. But then that one also reacts with more hydroxide and gives us 1 plus. And we could go probably even a step further and get a neutral FeOH3 molecule, and I think that tends to precipitate out pretty nicely. But that type of reaction, sometimes it makes sense to go ahead and look at two of those at the same time and say, well, they both happen in sequence. They are both technically in equilibrium, but what we really care about is going from Fe3 plus to FeOH2 single plus, right? That kind of a scheme. So in that sense, sometimes it makes sense to do sets of reactions. And so what we see here is exactly that, where we have the K, and it labels it as H1 here and KH2 here. So for each of these sequences, we can define a K value. Now, once we want to put them together, we could add them up in terms of summing the whole reactant set and the whole product set, put each of those terms on each side and say, okay, this is the full equation, and it could simplify down a little bit, and you'll notice that it will simplify. We have an FeOH2 plus here, an FeOH2 plus here, and that's going to take out the intermediate step, essentially. When we do that, if we treat this like any other equilibrium system that we've done so far, we will notice that in order to, before we simplify it, we would get, and writing it up as the products over reactants, we get something where it looks a little bit like this, where we have FeOH here, FeOH, combining all those together, it would be the same thing mathematically as just saying, instead of writing it all out like that, is to say the K for this combined one is just K1 times K2. So we could do it very elaborately and set it up appropriately, or we just notice that's kind of a shortcut and we can simply say it's K1 times K2 here. That's kind of the point. All right.
This is concerning like multi-step reactions with like rate determining steps.
This is not dealing with rate determining steps, but that's probably where you've seen this type of a situation in the past. Since we're not doing really kinetics at the moment, we're not dealing with one single rate. This is an equilibrium constant that's, because we're doing two rates both ways. This is the, like, that is a relevant context of probably where you've seen this kind of stuff. Okay, what is the rate determining step? And that's going to be the K, that, like, the rate constant that matters. So in different areas, we will look at combining chemical reactions. Say, okay, we're doing this, and then it's going to here, and then to there. And in that sense of the rate limiting, you might find one that's really the important one to see if you can speed up that one, you speed up the whole process. Here, we're just talking about things that happen pretty quickly, but they're all in equilibrium together. So if we wanted to know something about Fe3 plus and the FeOH2 single plus, if we wanted to know something about those two combined into one simplified reaction that looks like this, that's when it becomes convenient to say, okay, the overall equilibrium, if we kind of skip out the middle parts, looks like this, and we want to know the K for that overall system. That's why we do this. Another good question there. Okay, so kind of pretty straightforward when I say it that way, but I think that's not necessarily intuitive till we stop and think about it. The same is true if we divide, or subtract rather, then we can divide. So if we were subtracting two equations to simplify, we can do the same thing, except we're dividing the K's. And this would be also the same, you know, when we subtract something like this, it's kind of the same thing as if we were doing, instead of having two systems that were in the addition case, it was kind of like we had in the first one reactants and products in equilibrium, and in the second one reactants and products. In the subtraction, it's almost the same thing. In fact, we could add as long as we are flipping those. And I'll explain in just a second. So in the addition, we take 1 plus 2. In the subtraction, we could do 1 plus 2, but flipped. And what I mean by that is we could say reactants in equilibrium with the products. And then we could add to it, if we wanted to, the products on the left side in equilibrium with the reactant. So if we just flip that around, it's the same thing as subtracting it. So that might just be more confusing than it's worth. But the way we manipulate these, the way we're piecing them together in order to find a simple form of something, that's kind of how you can do it one way or the other. So in this example, we have the first reaction is the one we just talked about. We have Fe3 plus. This is actually from the previous slide, right? We had combined these two to get our new K for the overall equation of Fe3 plus in equilibrium with this FeOH2 plus. And now we might want to say, well, what happens when we include water, the equilibrium reaction with water, to try to simplify or to remove the OH minus and get it into H plus form instead? so that we can look at this from an acidity perspective instead of a basicity perspective. So that's what this piece is doing. So essentially, we are going to substitute with the equilibrium of water to get H plus. So we're going to include the Kw, the water equilibrium reaction, which normally we would write as H2O is the reactant in equilibrium with H plus and OH minus. Right? So in this case, we are flipping it so that when we put it together properly, it works. Okay, so the final situation here then is Fe3 plus 2H2O is in equilibrium with this FeOH2 plus 2H plus. And that's where we get that division of the Kw at the end there. Yeah.
So I'm just a little bit confused. I get how you're reversing the reaction so that you can cancel the hydroxides, but whenever you reverse the reaction, does it not take the inverse of the equilibrium constant, and then later on I see that it's divided by Kw to the minus 2, which then reduces to multiplying by Kw to the 2, but I'm just sort of confused. Like why is it not flipped?
Okay, so what you said partway through there, I think, is answering the question. You invert the equilibrium constant if you were to flip them,
Right.
and so that's like dividing by it. So when I may have confused things a little here the way I wrote it, but if you wanted to just multiply everything, then you invert that equilibrium constant and multiply.
Okay. Yeah. Okay. Yeah.
So let's not pay too much attention to what I wrote here. I think you can kind of understand what I was trying to say is we can flip it, and that will invert the equilibrium constant, and it works the same way as adding and multiplying, all that. It's all just looking at the fact that we define our equilibrium constants as the products over the reactants in terms of their activity, right? So products over reactants. And recognizing that if we were to flip around our arrangement of things, then that's going to invert that K because we flipped them. So don't worry too much about that. Just wanted to let you know that in some cases we might have to subtract, like in this case, and then we get that division. Now we will notice there's a 2 here for the water, so we end up getting the 2 here. Now what you will see is in order to make this arrange nicely, they did a subtraction and they flipped it, and so then there's a negative here. So ultimately that became this multiplied by K squared. So
flipping the reaction would like make it back into an addition problem essentially.
Yeah, so I don't really know why they didn't just add it like a normal. Maybe they were just showing that you could do this the same thing with subtraction and addition. So you could probably just write it this way and do it as an addition problem. Right? So if you wrote it that way and you ignored this for a second, and this is just K equals Kw squared, then you add everything fine, it multiplies across, and you're all good.
Yeah.
So I think they've just made it intentionally a little confusing to illustrate the point. And I didn't catch that that's what they were doing till just now. But I got worried there for a moment that I had said something wrong because I didn't notice the negative here. And I was like, don't pay too much attention. All right. Did I confuse you all the way, or just do you kind of get it? Only a little bit of confusion? We okay? Can just ignore it for now? Figure it out later? Okay. So I'm going to clean up the notes just a little bit here. The point is, we can flip around the equations, but of course we will follow what that does to the equilibrium constant. Okay, that means we can add or subtract. We just have to adjust with the equilibrium constant appropriately, how it works out algebraically. When in doubt, trust your algebra. Okay. So maybe doing a little example can be an easy way to check and apply that. So here we have 3 reactions, and we want to know the sum total equilibrium here. So take a moment and solve this. It says consider the first 3 reactions with their K values at 25 Celsius and 1 atmosphere. Don't worry about the little asterisk. We'll talk about that later. And we can call these K1, K2, and K3, and K4. So we're solving for K4. And we have those 3 reactions. so I think most of you have had a chance to get a look at it, see if you have the right thing. If you'll notice what I did before I reminded myself of the solutions, I started writing up the 3 reactions and to look at, do I need to add them, subtract them, like what am I doing with them in order to get them to combine correctly. And so I got to this point and I just paused so I could kind of explain my thinking. As I was double checking, did I do this right with the first one plus the second one minus the third? I want CO2 on the left, of course, because I need to match this. So I have CO2 plus H2O, but I'm going to minus H2O on the left side of this reaction, so that'll cancel. And then I'm adding an H2CO3 here, but actually that's going to cancel with what's on the right side, so I scratch that. Those two should cancel. And then on that should be it on the left side. And right now I'm not paying attention to my target, I'm just paying attention to the way I wrote it up and what's happening on this. So on the right side, it looks like I'm going to have H plus and then minus an H plus. Those will cancel. And then I'll have a HCO3 and then a negative OH. Okay, so what I ended up with here was HCO3 minus and then minus an OH minus, which is weird. We don't normally subtract, so that's just going to move over to the other side. And now that I look back on the other side, like back over here, that actually looks good, right? Because that should take that OH minus right where it needs to be. Okay, so that means we should do K1 times K2 divided by K3, right? And so then if you put that in the calculator correctly, then that should get us to, got that correctly, 1.5 times 10 to the 6. Okay? All right. Make sense? Any issues? Cool. Okay, so I'm going to spend the rest of the class period talking about activity. That includes ionic strength, which you probably have seen before. Real quickly, when I say activity, this is coming back to that idea that sometimes a chemical can be quite, let's say 1 mole concentration, 1 mole per liter, but it's not acting like it. And the reason that can happen is different forces might be involved to help shield it. It's one molecule might be stiff arming from the other ones based on their charges. Or maybe they get surrounded by other ions that then kind of act as a barrier, a little force field, to prevent it from interacting with other molecules like it would normally. So the activity, the effective concentration is that activity. That can vary based on what's around. And most of our chemistry we're going to deal with, thankfully, is in freshwater systems, in terms of, let's say, water treatment, a lot of wastewater treatment even. It can have an impact, but usually it's when you have a lot of salts, a lot of interesting stuff in the water, that you get some different things happening. So the point of kind of talking about it is to show you that there are important corrections we can make, even if we're going to spend most of the time setting that aside and saying, okay, we're going to assume that we have that molar concentrations are going to be fine to use. Kind of like what we talked about with, we can look at concentrations in molal, moles per kilogram of water. Technically, that would be slightly more accurate sometimes, but typically we're just going to go with molar. Okay, so the reason it can happen, as I mentioned, if you imagine, let's say, H+, and you've got chlorides around it, that's going to be a lot. Could be, so that could be one case where you have H+ and Cl-, and maybe the acid, so A-, that could be Cl, if it's hydrochloric acid. It could be any type of acid with a minus charge after it's given up that proton. And you have sodium around it. Well, compare that to if we had magnesium chloride. So now suddenly we have Mg2+, and we only need, how does that interact with this acid? It's going to interact differently because there's 2 charges instead of just 1. So the charge environment is going to be a lot different. So if you had the same amount of magnesium versus sodium, the magnesium is going to have a much bigger charge impact. So the type of charge we have around, the amount of charge we have around, can make a big difference. So if each of these were Mg2 plus, that are kind of crowding around the negative charge, we can see they would be satisfying more charge and changing the dynamics of what's going on in solution, just overall. Okay, so that shielding concept is kind of what I'm referring to. There are, of course, ions. Let's say sulfate. So sulfuric acid will release sulfate. That is an example of an anion that has multiple charges. It would also be relevant. There's other sulfates we could look at. So the charge is important. So how do we quantify the charge itself? Well, there's a concept called ionic strength. And this is, in a way, we're quantifying the concentration of electrical charge. That's what ionic strength is kind of giving us. So we need to know something about that, or have some tool to describe that, and ionic strength will be the term we will use. So I for ionic strength, it's equal to half of all of the charges in solution. And when I say that, I'm saying for a given species I, its concentration times the charge of I squared. So for example, if we had magnesium chloride that was added to water and gives us Mg2 plus and 2Cl minus, then we end up with some magnesium with a 2 plus charge and chloride. So for a solution like that, our ionic strength would be 1/2 times, and we're just going to sum it using the sum here, but really all we have to do is do this charge times its concentration. It's charge squared, z squared, z is the charge. So it's concentration times its charge squared. That keeps us in positive territory, which is nice. And just do that for each species. So in this case, we could say this is going to be 1/2 times the concentration, molar concentration of magnesium, times its charge, which was +2 squared. And then we are summing all of them together, so we're adding the next one in line. Next one is chloride. So we're going to add the chloride concentration times its charge, which is a -1. But we're going to square that, so it's just like multiplying by 1. Okay, so that's how we would prepare the ionic strength equation for a simple solution like that. We might have multiple sources of magnesium or chloride if we're just adding a bunch of salt, but we will have one final concentration, right? So what we're doing is we're looking at the final concentration. That's what really matters here. Okay, does that make sense? So this one's pretty straightforward. We just have to make sure that we are attending to the charges and all that. Yeah.
Does the stoichiometric coefficient have any bearing onto the ionic strength?
So it's a good question here. So you're asking about the stoichiometric coefficient, the 2 right here.
Yeah.
That has a bearing on your chloride concentration. Therefore, it has bearing on that. So when I'm saying like there might be multiple sources of it, or when you add magnesium chloride, let's say you add a gram of magnesium chloride and a gram of sodium chloride. You have to account for that stoichiometry to know your chloride concentration. So yes, but it's already accounted for since we're doing the concentration here. Yeah, and that's exactly the type of thing you could miss. So it's, again, thank you for that question. Okay, so give it a shot. Do 100 milligrams per liter of magnesium chloride. Calculate the ionic strength for that. Also, go ahead and give me the concentration for magnesium and chloride.
So to be clear, we're not going to be using an ice table for this.
An ice table? What do you mean?
Like initial change, equilibrium.
not familiar with what you're referring to.
I'll tell you about it after.
Okay. Yeah. All right. So I put up the answer up here. walk you through it real quick. I put it in Excel. First, we need to find out what molar concentration we have for magnesium and chloride, right? And the way I did that was I said, okay, we have 100 milligrams per liter of MgCl2. We weren't given anything about it, like not dissolving. So kind of the implication, and in fact, that forward arrow means it's all going to dissolve, essentially. Weren't doing anything with the equilibrium there, just adding it. We have 2 Cl minus for every 1 mole of that molecule that we dissolve. So what I did was I said, well, let's just go ahead and say as if it was staying as MgCl2, I'll find the concentration, so to speak, of that and go from there. So we could find how many moles of that we added. I just left it in moles per liter. So I said we have 100 milligrams per liter, that's 0.1 grams per liter. And then if I take that and I say 0.1 divided by the molecular weight, so that'll take us from grams per liter dividing by grams per mole. The grams will cancel and that'll flip the moles. So you just have to make sure you're doing that in the right order to get the units right. You should get an answer with moles per liter of MgCl2. So even though we don't normally report it as the concentration of something that dissolves, you might call that the formula weight or the formula concentration. Anyway, that gives us the amount of moles per liter of that we dissolved, which was 0.00105 moles per liter of magnesium chloride. So for every 1 mole of that we dissolve, we get 1 mole of magnesium. And so that's the concentration of magnesium in solution. And for every 1 mole of that, we get 2 moles of chloride because of the Cl2. And so therefore, we have twice that amount for our chloride concentration. And then we can put it into the ionic strength equation. And we see it's 1/2 times the sum of each concentration times its particular charge squared. That comes out to be that 0.00315. Okay. Does that make sense? Any trouble on that? Yeah.
I got like something different. I took like the 100 milligrams per liter, multiplied it by like a conversion to convert to grams, and then like did the molecular weight and then some moles, and like I got a different answer.
What'd you get, or what?
For magnesium, I got 0.0041 moles per liter, and then the other one I got 0.0028. So it's like kind of similar for the second one, but like I feel like isn't that not like is that the wrong way to do it?
What you described sounds like the way I did it. So my question for you is, did you take the magnesium and the chloride, these values, like their atomic weights separately, or did you find the molecular weight of MgCl2, which was 95 point whatever?
I did them both like separately.
0.21. So when we add magnesium chloride, we have to figure out, we can't separate it yet. We have to figure out the number of moles of that we dissolve and then split it. So if you went ahead and said you had 100 milligrams per liter of magnesium and went from there, and then 100 milligrams per liter of chloride and go from there, you missed the fact that they started as a combined thing. Yeah. It's a little weird to describe it as 100 milligrams per liter of something that dissolves. Like that itself is a little strange way to phrase it. I could have, or perhaps should have said, we add 100 milligrams of this to 1 liter, right? Then it makes a little more sense. All right. Okay, so then once we have an ionic strength, what can we do with it? How does that relate to this activity coefficient that we've mentioned? Well, here's where the math gets a little more complicated, and we can do some calculations. We can take a look at how people have adapted these. And I'm really just here to show you there's a simple method, a slightly more complicated method, and then one that extends it out a little further. And I'm going to show you a graph why and how this could matter, when it matters, just to give you an idea of, well, make sure you've seen it before, let you know you could have the confidence that you can calculate this if you need to, We just don't need to do this on every chemistry exam, right? Just because we can doesn't mean we have to do it every time. Okay, so the simple version here is the Boltzmann distribution. This is coming from, so the Boltzmann, this is kind of physics and electromagnetism just saying, okay, here's how things arrange. If we distribute charges within an environment, here's some information about how they're going to interact. And so this version of our activity calculation is going to take kind of a simple approach, and that's saying log of this activity coefficient. So remember this, this gamma. Let me see. I think I draw it, yeah, like that. So gamma I, this is the activity coefficient for I. And remember, we defined activity. So A for some I would be that activity coefficient times the molar concentration of whatever species I we're talking about, right? So when I'm talking about these, when we see these little gammas, that's the coefficient that would multiply against our molar concentration to give us the total activity, where this A is our activity. Okay, so basically we're just solving for some constant that goes in front of our concentration. So we have log of that activity coefficient is equal to negative A, talk about that in a second, times Z, which is the charge, squared, times the square root of I being the ionic strength. Okay, so we just solved for ionic strength. We've got that. We know how to deal with a log term. That's no big deal. We know the charge, and we square it. This A, then, is some constant depending on the pressure and temperature. So that would be maybe in a lookup table, and perhaps that's something that you were referring to earlier. That might be where that would come in. We would need some table or some other calculation here. Maybe it's just given, right? So A being some constant. Then we know how to solve for I now. We just did that. We can find this activity coefficient with this equation. Okay? This will work for some cases. Next up, if we need to be a little more complicated, maybe if we need to go into higher ionic strength territory, we use the Debye-Huckel, something like that, equation. And this is just adapting it a little bit further. And what you see is it's basically the same, except we're going to divide by 1 plus the square root of ionic strength. So we're taking into account some little extra part here. And perhaps a little more formally, we could say this is 1 plus B times this new A naught, but the deal is this B and the A naught, theoretically, they're approximately 1. So we can kind of just simplify. So like I said, we don't need to get into the nitty-gritty of why and how all this is derived, except that it's from kind of a physical principle of here's how charge is interacting. Somebody has already kind of shown all that, and we're building our understanding of how our charged ions in solution are going to interact with each other and how that's relevant here. Okay, so that's this equation. It kind of simplifies to almost the same thing, and everything we had in the previous, the Boltzmann distribution style or equation would work here, assuming we've got that B is a constant and B times A. This little a should be about 1. Then we're good. Okay, so maybe for some really, really large atom or molecule, maybe that's when it's relevant and we'd have to change something a little there. Okay, then higher ionic strength. So when we really go higher, this is where we go to what we would call the Guntelberg or the Davies equation. And I think Davies is a subset. So here, it's essentially, again, the same basic thing, except we are adding a piece with another B. I did not choose these letters, so you can blame the book I'm taking from. Lowercase b times I, and this is some either a general or a specific constant, I guess based on the application, perhaps on the species we're looking at. In the case of the Davies equation, this is set to 0.3, and that's just that. That's the Davies equation, okay? And so all this to say there are a few equations we can use, and they are useful in different scenarios, and here's why. So if we take a look at a graph where we are looking at a log scale of ionic strength, so higher and higher ionic strength, meaning we're going to seawater and beyond as we head to the right. So if we look on the left, this would be pure water down at 0, and this would be like beyond seawater, like Dead Sea territory or something like that. So very salty, very, very high in ionic strength. Okay, and what we see here, these 3 different models will give us an ionic strength and based on this, and we see the ionic strength tends to drop as we get, the activity coefficient tends to drop. This is activity for calcium, by the way. Will be dropping as we go from pure water down towards very salty water. So one thing we note is the equation 2.9. I think that's the simplest version. Did I label them? Didn't leave the labels. But I think this should be the Boltzmann one. It goes to basically 0 at some point, which is not probably realistic. It's probably still some activity. So that the equation itself kind of fails us once we get up to high ionic strength. The next one, I think this would be the Debbie-Huckel, something. I think that's correct. I could have this backwards. But we see that one works pretty well. This is probably extended one because this was the one that goes crazy over here. The Davies equation can also be called an extended Debbie-Huckel. I think then that would leave this guy to be the other odd man out that probably doesn't work because we see the activity shooting up at some point, right? So I think that's probably not a sufficient explanation of that true activity. Either way, what we see is things can go wrong with some of the models. I'm not gonna, don't even try to think about which one's which here because I'm not confident enough. But I'm just saying the 3 different ones are here and they're useful in different conditions because the models are gonna go crazy at some points, right? So what we'll probably do is usually use the Davies equation. Or be given, say, hey, use this equation, here it is, to solve for something, right? Given that we can solve for the ionic strength, and we either can look up that value of A or be given it or something, then you can solve for the activity coefficient, and it's just a little bit more math on top of what you've been doing in order to solve the chemistry problem, right? So all of this can go into any of our equilibrium reactions, and you see how that can actually be pretty important. If we're looking at an equilibrium reaction in seawater, seawater I think is in this range, we can see how that's a lot different than fresh water. So there are certainly cases where we would need to account for them. In some situations, all 3 give a very similar result, right? There's not a big difference in freshwater systems if we are defining them, let's say here and beyond. Brackish systems, it starts becoming important, and seawater, we can definitely see sometimes it might be very important. Okay, so we've only got 5 minutes left, so I think I'll just read this problem out in case you wanted to work on it, and then I'll give it some thought. Maybe I'll put this as a homework problem or something like that. But this problem gives us some data from the Rio Grande at Laredo. Has the following composition, and it's giving us all these different ions and chemicals in milligrams per liter and millimoles per liter. Then it asks us what's the ionic strength, what are the activity coefficients if we use the extended Debye-Huckel, and then how much is the water undersaturated with respect to gypsum. So kind of connecting all these pieces that we've been talking about. Okay, I'm going to leave it off there. Any questions before we go? Have a good day. We'll see you on next Tuesday.